Welcome to the module on Modeling of Earth Science and Environmental CalVal products. A mathematical model is a description of a system using math concepts and language. The process of developing a mathematical model is termed mathematical modeling. Math models are used in the natural sciences, such as in physics, biology, earth science, and chemistry, in engineering disciplines, such as computer science, electrical engineering, and in the social sciences, such as economics, psychology, sociology, and political science. Math modeling is the process of using various mathematical structures, such as graphs, equations, diagrams, scatter plots, tree diagrams, and so forth, to represent real-world solutions. The model provides an abstraction that reduces the problem to its essential characteristics. When used in problem solving, mathematics may be applied to specific problems already posed in mathematical form, or it may be used to formulate such problems. So how do we model a physical system? Let's try to understand modeling through a simple problem. What will the temperature of a pot of water on the stove be as a function of time? So what do we need to know? Well, let's set up the initial conditions. What is the water temperature at the start of the problem? Let's assign that initial temperature TO. We need to know how large and how hot is the stovetop. We'll assign that variable F. How much water is in the pot? We'll assign that variable the letter M. We need to know the properties of the water, such as how much heat it takes to raise the temperature of water heat capacity, and give that letter C. And we need to know how much time has elapsed. And we can choose this, and we'll give this small letter T. So how does this information relate to the temperature of the water? The temperature is equal to the initial temperature plus the rate of temperature change times the time elapsed, where the rate of temperature change is equal to heating strength divided by water mass times heat capacity. So if you put all the variables together, the temperature is equal to the initial temperature plus how hot or large the stovetop is divided by how much water is in the pot multiplied by the heat capacity of the water, all of that multiplied by how much time has elapsed. We can then repeat this time step. Time stepping is more important in systems where the change in the system depends on the state of the system. Does this sound right? Yes or no? Now let's go back to our pot of water. What does our simple model say about the temperature of the water after a long time has passed? It says the temperature increases indefinitely. Is the equation right? Some of you will say yes. But does this really happen? We've missed something that happens as the water approaches its boiling point. For any system, we can say that the change in energy is equal to the energy into the system minus the energy out of the system. So if we rearrange our simple model into an energy perspective, final energy minus initial energy is equal to the energy that you put in the system initially. The energy change is therefore equivalent to the energy that you put into the system. So our initial model neglects energy out of the system by evaporating water. An alternative simple model is that the energy of the system is constant and that the system is in equilibrium. So bringing it back to our pot of water, we will reach a steady temperature when the energy into the system is equal to the energy out of the system, or the energy from the stove is equal to the energy lost by evaporating water. This occurs at the boiling point. So from our small experiment, we also learned that for one system, multiple models can apply. In our case, there were two models. The transient model, where the system is evolving, as depicted by the temperature rising exponentially, and the equilibrium model, where the system is in balance and steady. Equilibrium models are useful because they identify the state the system wants to be in. So if we apply the simplest equilibrium model to the Earth, the equilibrium temperature of the Earth represents a balance between incoming solar radiation and outgoing long-wave radiation. So let's understand model building processes. A black box model is a system in which there is no a priori information available. In black box models, One tries to estimate both the functional form of relations between variables and the numerical parameters in those functions. The opposite of a black box is a system where the inner components or logic are available for inspection, which is most commonly referred to as white box or physical modeling. In the physical sciences, a traditional mathematical model contains most of the following elements. 1. Governing equations. 2. Supplementary submodels, such as defining equations and constitutive equations. 3. Assumptions and constraints, such as the initial and boundary conditions, as well as the classical constraints and kinematic equations. The watershed model and the general circulation model are two basic examples of physical mathematical models. This slide is a flowchart that shows the relationship between experiment, simulation, and theory. This slide talks about variable selection in model building. You find the most effective variables through dropping and adding variables one at a time. However, one at a time adding and dropping of variables makes it possible to miss the optimal model. This slide shows a 6-step approach to modeling dynamic systems. You begin by defining the system and its components. You formulate the mathematical model and list the necessary assumptions. You write the differential equations describing the model. You solve these equations for the desired output variables. In step 5, you examine the solutions and the assumptions. And in step 6, if necessary, you reanalyze or redesign the system. Some models represent processes while others are spatial representations. Under process representation, they're physically based models which are derived from equations representing the actual physics of the process, conceptual models which capture the essential processes, empirical and regression models, and stochastic models which evaluate historical time series based on probability. The lumped model considers each watershed as a single aggregate unit with model parameters and inputs applied to the entire area of each watershed. Distributed hydrologic models feature the capability to incorporate a variety of spatially varying data from a proliferating set of databases on land use, land and soil characteristics, high-resolution precipitation, temperature, and other forcing inputs. A lookup table is an array that replaces runtime computation with a simpler array indexing operation. The savings in terms of processing time can be significant since retrieving a value from memory is often faster than undergoing an expensive computation or input-output operation. In climate modeling, lookup tables are used to generate pre-computed theoretical outputs based on radiative transfer climate modeling. Exogenous variables are quantitative variables whose values are determined external to a symbolic model. Endogenous variables are quantitative variables whose values are determined by the relationships of a symbolic model. In this watershed model, Q is the endogenous variable, and C, I, and A are the exogenous variables. Sensitivity is a metric used to characterize the response of the model system to a given forcing variable. Data are numbers that reflect quantitative facts about the environment. They are a paradox because decisions are based on the interpretation of the data, but data are also gathered through models designed by the decision. This leads to the question of which came first, data or models. Both can come first. The gray box model combines a partial theoretical structure with data to complete the model. This slide shows examples of physical models. Empirical models are based on empirical observations rather than on mathematically describable relationships of the system being modeled. Calculations in semi-empirical models are based on a combination of observed associations between variables and theoretical considerations which relate variables through fundamental principles such as the conservation of energy. For example, in sea level studies, semi-empirical models refer specifically to transfer functions formulated to project future global mean sea level change or contributions to it from future global mean surface temperature change or radiative forcing. Machine learning is the science of getting computers to act without being explicitly programmed. Machine learning is a subset of artificial intelligence in the field of computer science that often uses statistical techniques to give computers the ability to learn, i.e., progressively improve performance on a specific task, with data without being explicitly programmed. Within the field of data analytics, machine learning is a method used to devise complex models and algorithms that lend themselves to prediction. This slide shows a list of machine learning algorithms that exist today based on the types of statistics used. Multiple regression analysis is a powerful technique used for predicting a continuous dependent variable from a number of independent variables called the predictors. Here, B0 is the intercept, and B1, B2, B3, all the way up to BP are analogous to the slope in the linear regression equation, and they're also called the regression coefficients. They can be interpreted the same way as a slope. Thus, if b1 is equal to 2.5, it would indicate that y will increase by 2.5 units if x1 is increased by 1 unit. So how good is the regression? Once a multiple regression equation has been constructed, you can check how good it is in terms of predictive ability by examining the coefficient of determination, also known as r squared. R squared usually lies between 0 and 1. The closer r squared is to 1, the better the predictive ability of the regression. Neural networks are a set of algorithms modeled loosely after the human brain that are designed to recognize patterns. They interpret sensory data through a kind of machine perception, labeling or clustering raw input. Fuzzy logic is an approach to computing based on degrees of truth rather than the usual true, false, or Boolean logic on which the modern computer is based. A fuzzy logic model is also constructed by a set of if-then rules to describe the relationship among the input and output variables. As shown in the figure, fuzzy clustering, also known as soft clustering, is a form of clustering in which each data point can belong to more than one cluster. Cluster analysis involves assigning data points to clusters such that items in the same cluster are as similar as possible, while items belonging to different clusters are as dissimilar as possible. Clusters are identified via similarity measures. These similarity measures include distance, connectivity, and intensity. Different similarity measures may be chosen based on the data or the application. Now we're going to turn to climate modeling. Climate models use quantitative methods to simulate the interactions of the important drivers of climate, including the atmosphere, oceans, land surface, and ice. They're used for a variety of purposes, from the study of the dynamics of the climate system to projections of future climate. All climate models take into account incoming shortwave solar radiation, which includes ultraviolet, visible, and a limited portion of infrared energy. Climate models also take into account outgoing or long-wave radiation. Any imbalance between incoming and outgoing radiation results in a change in temperature. Climate models are basically equations that are believed to represent the physical, chemical, and biological processes governing the climate system for the scale of interest. They can help answer what-if questions. For example, what would the climate be if carbon dioxide doubled? What would the climate be if Greenland ice was all to melt? Over the past 25 years, different components have been added to the climate model to better represent our climate system. This slide shows the components that have been added through the years. Climate change, also referred to as global warming, is the observed century-scale rise in the average temperature of the Earth's climate system and its related effects. As shown in the figure, multiple modeling scenarios show that the climate system is warming. Uncertainty over the effect of feedbacks is a major reason why different climate models project different magnitudes of warming for a given forcing scenario. This slide shows a sample of climate model coding to show you how the code is written. This slide shows the MM5 model. MM5 stands for the 5th generation Penn State NCAR mesoscale model. It's a regional mesoscale model that is used for creating weather forecasts and climate projections. While simple hydrologic models are limited by assumptions and calculations, more complex models allow us to better approximate different parts of the hydrologic cycle. We can see from this slide that a hydrologic model may take into account a complex array of natural and human influence factors. In this model, we see the input and movement of water through an idealized hydrologic system. This slide shows 3 modeling approaches for the same watershed. This slide shows the model for flash flood forecasting. There are also models for vegetation, such as the one shown on this slide. Models are evaluated by testing them against observations both past and present. You can also compare different models with each other. You can also generate metrics of reliability, and for weather models, you can compare numerical weather prediction to the weather model. There are limits to evaluation, and these include unforced or internal variability, availability of observations against which to compare the model, the accuracy of those observations, and the accuracy of boundary conditions. If you have any questions on this module, please contact Dr. Tarendra Lakankar.